Thank you all, and thank you to Professor Li and Professor Wu. I'm very glad to present my work with Gangchen and Ying Zhang, which is about the panel data modeling and computing. I will give three parts. The first one is what is the panel counted data, and the second one is the statistical models about the panel counted data, and the last one is we give an efficient algorithm for computing the model for the non-parametric maximum likelihood estimates and semi-parametric maximum locally likelihood expansion. First, let me say something about what is the panel counted data. Panel counted data is about the sample data. Originally, the sample data is ignore the time when the sample is sampled. The data is sampled. But in the social work and in the medicine, actually, the sample data is sampled always at different time. It means the data maybe reflect the object at different time, and actually they are different. But traditionally, in the parameter statistics, they are the same. But now we treat the data in the names of panel data. It means the observation of multiple phenomena repeated, obtained over multiple time periods for the same firms or individuals. So this is the same people or same object. The behavior are recorded at different times. This is a very simple example. Means we have two persons, and we recorded their data at different time, but the age is different, the income is different, also the sex is the same. Now we are pay special attention to the panel counted data. The panel counted data is a special type of panel data in which we have special interests on the counter. It means there is an underlying counting process, which means that especially in the biomedical, we can trick some disease. The number of the patients, special means SARS, special means HIV, special means Ebola. Then we can record it how many people are here, how many patients have been treated or how many patients come to the hospital. So, especially the follow-up study. For the panel count data, what we want to know is the exact times at which recurrent events occurred. This is what we want to know. But actually, we can observe is the number of events that happen between consecutive observation times. It means that we cannot record it when it is happened, but only when it is happened, then the patient will go to hospital and say that I have a disease. So this is the difference, and we also want from this one to estimate the exact times. There is many works on these problems, especially in two ways. One way is non-parametric methods. The second way is semi-parametric analysis. The semi-parametric analysis normally using the proportional mean model. Proportional mean model. The mean is, which means that we just focus on the expected number of a random variable. And in the computation, this is the model, statistical models. In the computations, this work, the two methods, there are also no parametric and semi-parametric methods based on the no homogeneous Poisson problem process. This one is first give the idea to use non-homogeneous Poisson process to model the process of the panel data. And they also use the interactive convex monoreturn algorithm to compute the non-parametric maximized likelihood estimate. This method, can be time-consuming when the sample size is large and the observation time are very different among study subjects. It means that different people at different time to the hospital. They are not at the same time that many people come here. In Hu's work, they studied the MPMLE using EM algorithm The EAX algorithm is a very popular algorithm which is easy to implement it, but its convergence is slower than the ICM algorithm. And in this work, they use the extended ICM algorithm to compute the regression parameter and baseline mean function jointly. It is also a semi-parametric maximum likelihood estimation problem. This method requires enormous computing effort to achieve the convergence. It means that it's somewhat also time-consuming, even for moderate size data. This is the work have done. Now, in our work, we propose some traditional Newton-Raphson method. It's a very traditional method. We from traditional Newton-Raphson algorithm to have a new algorithm to compute both the MPMLE and SPMLE of the panel count data. Our algorithm can greatly reduce the numerical effort compared to the existing ICM time algorithm, and therefore we have enough time to compute the maximum likely expectation of panel count data, which means that since this and this algorithms has some problems in efficiency, in convergency, so it's not a popular method. Use the MPMLE and SFMPLE to analyze the panel count data. With our method, we are being encouraged to use these two methods to analyze the data. But in this presentation, I will focus on the MPLE of panel count data and its computation because of the time. Now, I would give the statistical models. Here's some notation. N is a univariable counting process. It means we just record the number of the object. And this is the sample, which means that N is the number of events observed at k random times, which means k random times means we keep one people or keep one patient. We record when it is come. And the time is t k 0 to t k k. K is also be random as well. Then we use D to represent K, T, N, all these samples for each subject. And D1, Dn means they are IID copies of D. So IID copies of D means that different people's behavior are the same. From this observation, what we want to know is that lambda t, which is the expected value of nt. This is what we want to know. This also means the mean function. This is what we have done, say that the mean function. The Poisson process model is very simple, since the Poisson distribution, it means that the number of the observation between Tki to Tki minus 1 is n Tki minus n Tki minus 1. The probability is in this way. This is normally the Poisson process, the Poisson distribution. For all subjects at all consecutive observation time, it means that we have D1 to Dn, all the observation, since they are IID, then we get all these samples. The probability is all the probabilities multiplied. We just multiply all these probability, then we can get this one. And as we know that the maximum likelihood estimation would be, we want to find out the parameter lambda Tki, I is from 1 to n, j is from 1 to ki, should be the value to maximize p. This is the basic idea of maximum likely estimation. And to make p maximum is equivalent to make log of p maximum. And log of p, we can transfer this multiple formula to sigma formula. And also let this one to here, and this one are the constant. So we can omit this one. Then the log p formula is very simple, the p formula. So this is the log likelihood function. Here, this is the examples. This is what we want to know. In the analysis, since the different subjects are ID, so we just order the distinct observation time points from different people. We just put them together. We just put them together and form ordered observation time from 0 S0 to Sm, and S0 is less than S2, and the largest one is Sm. So if we have disordered distinct observation times points, then the log likelihood for panel data would simplify to in the form of this one. This one is much simple than this, but we are introducing A and B. A and B, since they should be an identified function, which means then it's be 1 or 0. When these two conditions is satisfied, is 1 or otherwise it would be 0. And we also know that what we want to the parameters, not parameter, the lambda 1 to lambda m should great or equal to 0. This is the number, not real, but it's a number. To computing the maximum likelihood estimation, we should make L, the function L, maximize. It's very popular to use the generalized gradient algorithm. It will be in this form. If Lx is globally concave, then we just take Hx in this form. It means that it's a Hessian matrix, Hessian formula. It will lead to the widely used Newton-Raphson algorithm. With quadratic rate of convergence, it's a very popular method. But in our problem, we have two specialized points. The first point is that the quick convergence of NR algorithm is not demonstrated in constrained problems. What is a constraint? It means that all lambda is great or equal to 0. And another important issue is that this is the number of the patients at same disease we found. This should be in this order. So this is in the NP-MLE is not a generalized optimized problem. It is a constrained problem. So this is the new problem when we used Newton-Raphson algorithm. And another problem is that when we iterated the update xk plus 1 does not necessarily fall in the feasible region. The feasible region is that this one is this one, and this one is this one. So we cannot directly use the Newton-Raphson algorithm. We must modify it. We just use the projected Newton-Raphson algorithm. The projected Newton-Raphson is that we should make the update xk plus 1 in the feasible region modified by this one. Matrix Wx is a positive definite. If the feasible region and Wx is chosen and happen to be a positive definite matrix, then the algorithm will generalize a sequence converging to the true optimizer. It means that the projected NR algorithm will get the true value we wanted. Now I would say more about ICM. The ICM algorithm selects this formula to Hx. This method is good at the projecting can be easily implemented by finding the left derivative of a cumulative sum diagram in the paradigm of its isotonic regression. But it can be time-consuming when the sample size is large and the observation time are very different among studied subjects, as I have mentioned before. So our algorithm is that we take the cone C plus can into the linear inequality constraints. We can just take a matrix A in this way, then the projection can be easily implemented in the dual methods for strictly conventional quadratic programming, which have been coded in R package for public use, which means that in this step, we just use a very popular methods. We should not, like ICM, to make a very hardworking computing and to get the convergence. This is what we have fast computing time. So our algorithm's advantage is that quick convergence of Newton-Raphson methods. It means that we can get the same convergence speed as Newton-Raphson methods, and also the coding is very easy since we can use the R packages algorithm. But the condition is that the weight matrix Hx must be strictly positive definitely. And to satisfy this condition, we must modify the Poisson matrix, since Poisson matrix of the log likely will cause problem when we use it in our algorithm. So in our algorithm, we have some modification. One, to increase the log likelihood. It means that before we use Newton-Raphson methods, we have some constraints to lambda j, which means that if aj L is 0, then lambda j equals to lambda j minus 1. It's normal, since that it means that if there is no people to come here, and then the number is equal. And if Lj is 0 and Bj is 0, they should be satisfied. Then lambda j is equal to lambda j plus 1. This work is actually, it means that we can reduce the dimension of the lambda. This is what we have modified the NR algorithm. The second modify is sometimes by chance. If two adjacently distinct lambda values are too close, then the largest edge value would be overflow, or the smallest edge value would be less than 0. This is because of the computing process. To To avoid this problem, we replace the full matrix Hx by this one. It means that in Newton-Raphson's problem, this is in this way. Then in this way, it will cause the problem of if the adjacent distinct lambda is too close, then there will be some overflow problem or less than zero problem, so that we will change the Hx by this one. And this one is by chance. It means that if we find that some adjacent lambda is too close, then we would change the Hx. If they are not, okay, keep on. Actually, in our experiment, there is no more than 2% of times that such modification is needed. Now, I will give the detail of the projected Newton-Raphson algorithm. First, dimension reduction for the feasible region. 2, choose an initial value. The initial value should, to make this one is positively definite. This is the Newton-Raphson's algorithm. In the case iteration, calculate the smallest and largest eigenvalue, which is lambda 1 k minus 1 and lambda m k minus 1. If neither less than 1 or greater than 10 over 10, just keep the Hx like this, no modification. It's okay. Otherwise, we will modify this by this one. And with the h lambda k minus 1, then we would get b and get lambda tutor k by this formula. Now, this one is okay. This one is also a optimization problem. But luckily, the optimization problem is very easy, since, as we know, that this have been done in our package. So in this problem, we should know that it's lambda k. If this one is okay, then this one is okay. But if this one is not okay, otherwise, then we should get y. The y is the result of a linear search. If a linear search for this one. And here we should note that the epsilon should be between 1 and 1/2 to guarantee the value of the log likelihood increase sufficiently. So this is our algorithm. And finally, I would give the numerical study. We studied the problem by Monte Carlo simulation. Subject is sampled from 1 to 6. And given Ki, a panel of observation time are made as the ordered statistics from uniform distribution from 0 to 100. Given Ki and a panel observation and the panel observation time, the panel count are sampled from the Poisson process, Poisson 2 and T. This is our numerical studies. You could find that the number of iteration and the computing time, ICM is more than 100. We have 6, and this and this one, this and this one. No matter the number of number 50, 100, 200 is the number of the samples, which means that we have 50, 100, and 200 samples. And the number of the iteration, the number of the times is also good. This one, this one, this one, this one, this one, this one. And the standard, since it's a Monte Carlo simulation, so we should give this one. Get it? This one. It means that the deviation is also very good. Okay, and this is what I would say. It means I still have time? No? Oh, sorry. Sorry. Okay, thank you.
Okay.